To talk about measurements, we need to talk about something called a projector matrix. These are subclass of positive semi-definite matrices which we learned about last time. These were the matrices whose eigenvalues were non-negative. If I want to describe about all the different subclasses we have learned till now, let's make this rectangle which denotes all n by n square matrices. There is a big subclass of normal matrices here. These are all the matrices where I can apply spectral decomposition and mm star is equal to m star m. We can diagonalize them using an orthonormal basis. In this, we saw two categories: unitary and Hermitian. There is an overlap between these two. I will let you figure out what is this overlap. How can you characterize these matrices? On the other hand, we also saw matrices which were positive semi-definite. These were a subclass of Hermitian matrices, and the only positive semi-definite matrix which is unitary is identity. The only next class which is left to study is another subclass of PSD matrices, which I am going to call projector matrices. If I look at this hierarchy, normal matrices are the ones where eigenvalues can be anything. Any complex number is okay. Then I restricted it to Hermitian matrices where the eigenvalues could be real. Then I went to PSD matrices where the eigenvalues have to be non-negative. The next class is going to be projector matrices whose eigenvalues are just going to be two values, either 0 or 1. I will start by another description of projector matrix and then show that it is equivalent to saying that all the eigenvalues are either 0 or 1. The way I am going to define a projector is: a normal matrix is called projector if P square equal to P. A normal matrix, let's say P, is called a projector if this equation is satisfied. You have seen that for all these classes, we define some other characterization, and then we show that that definition is actually equivalent to some property of the eigenvalues. Same thing we are going to do for the projector. We define it like this: P square equal to P, but then spectral theorem will allow us to transfer this condition to some statement about eigenvalues. I want to convert this into some statement about eigenvalues. Let's do it. You will remember the definition, it's not very difficult. A matrix is called a projector if it satisfies P square equal to P. Since I know that P is normal, I can always write its spectral decomposition, which will look like this for some orthonormal basis xi xi. Let me calculate P square, or I will let you convince yourself that this is just squaring the eigenvalues. Another way to say it is, we have talked about operator functions, where we say that whenever you want to apply an operator on a normal matrix, the same operator is applied to every eigenvalue. Squaring is an operator. When I apply squaring operator on P, all my eigenvalues should be squared. So it's easy to convince you that P square is this formula. And now if I know that these two quantities are the same by uniqueness of spectral decomposition, I will get that lambda I square should be equal to lambda I. This will imply that lambda I is an element of 0, 1. We get another characterization. A normal matrix is called a projector if and only if all its eigenvalues take only two values. They are either 0 or 1. But what is the use? Why are we interested in these projector matrices? That will be clear once we see action of a projector matrix. Let's look at action of a projector matrix, and you will see that it's a very specific kind of action that allows us to use it as a measurement in the quantum mechanics scenario. Let's talk about the action. Remember, projector is a matrix whose eigenvalues are just 0 or 1. So I can write its spectral decomposition as this, where xi's are orthonormal. If xi's form a basis, then you can convince yourself that you will get identity. In general, when I talk about a projector, these xi's with high probability will not form a complete basis. The only time when they will form a complete basis is when I'm talking about identity. That is why you notice that this is not the complete dimension of the system. P is an n cross n matrix, but I'm only writing I equal to 1 up to k. Rest all will go to the 0 eigenspace. Let me clarify it more. If P has x1 to xk in the 1 eigenspace, and I can complete the basis xk plus 1 as 0 eigenspace, these are the only possible eigenspaces, then by spectral decomposition P will be xi. When 0 eigenspace is 0, then I get identity matrix. This seems like a very simple formula for the projector. What is its action? Say S is the space spanned by xi I equal to 1 to k. That is one eigenspace. In this case, notice that P of V is equal to V if V is element of S. That is because this if I write V as alpha 1 x1 plus alpha k xk, then PV will just apply. You can check when I multiply PV, x1 will only interact with the first term in my equation 1. I will get alpha 1 x1, alpha 2 x2 will only interact with the second term in equation 1, and I will get alpha 2x2 alpha k xk, which is my v vector itself. On the other hand, PV is equal to 0 if V is in the orthogonal subspace. That means V is an element of space spanned by xk plus 1 to xn. Other way to say it would be P acts as identity on S and 0 matrix on S perp. For a general vector V, let's say V is alpha 1 x1 to alpha n xn. Notice that I have taken a complete basis of my space. Now elements in one eigenspace, elements in 0 eigenspace, their linear combination, all of this. If I write PV, I will only get the part of the one eigenspace. So in English, I would say that P projects on the one eigenspace. And this is the reason why it is called a projector. We get one more characterization of a projector, and this time this definition is in one-to-one correspondence with the subspace. With the subspace of the entire space. So an n by n projector P for a subspace S of C to the n of our space is a matrix such that PV is equal to V. It acts as identity on any vector V in S, and it acts as 0 on anything which is orthogonal to it. Using linearity, this describes the complete action of P. In other words, P projects on subspace S. This will be our operating definition of a projector. We can talk about P square equal to P. We can say that eigenvalues are from 0, 1, or we can say that it projects on a subspace. You should remember all three characterizations. With this definition, the formula for P is very simple. If I say that on a subspace S, the projector is PS, then you can pick any orthonormal basis x1 to xk, and the projector would be this matrix. Not hard to prove. If you don't see it right now, take it as an exercise. Thank you.